So today we're going to go practical today, and we are assuming that you are given a district like this to design for the sewer and the storm. Yesterday, I said that the process of designing for sewer and storm are the same. And we also were able to define that sewer system is based on wastewater flow. And it's based on the water consumption. The major input parameter is the water demand per capita per day. While storm involves the hydrology of the area, which is the rainfall intensity and the catchment area involved. We also say that it is not all the catchment area that contributes to runoff when it comes to storm sewers. Rather, it is the impervious area. And for you to get the impervious area, you have to multiply the peak runoff coefficient with the total area. That is how you get the paved area or the impervious area. And that is that area that is a point of interest for us, because that is the area that cannot allow water to infiltrate, to percolate, to wet, to deep percolate, or to evapotranspirate. So this is a district we started, I told us yesterday. So this district is catchment A, catchment B, catchment C, catchment D, catchment E. Now, this is regular because it's a training, but in real life, it's not going to be regular like this. It could be shapeless, but whatever it is, just understand where the catchment, the flow is coming and where it's going to end. We said that if this is a sewer we are designing, it means that this point 4 will be the wastewater treatment plant. Then the river will now be somewhere close to it, so that after treating, the effluent will go to the wastewater treatment plant. After the removal of the BOD, the COD, the phosphate, the nitrogens, and maybe some few phosphorus, the water will now go to the water receiving, to the natural body, water body. Then if it is a storm that you are designing, it simply means there's not wastewater treatment plant, but the water will simply go into the open water body, provided there is not much the suspended materials or the contamination is not too much. So if you are given this, we said the first thing you do is you bring it into a table like this. So you can relate these two. Catchment A, pipe B, pipe C. So this pipe A is also representing catchment A. So while this boundary is a catchment, which is represent an area, this pipe also represents A. So all the waters, all the houses here, they are contribute their runoff to this pipe. All the ones here will contribute the runoff to this pipe. All the ones in C will contribute their water to C. So we said that you should take note that one catchment can also transfer water to the next catchment. So if you come to this one now, catchment A is giving water to catchment B. Okay, whether it's stormwater or sewer, is giving water to catchment B. Catchment C is giving to catchment D. That will be assuming that we have a closed boundary here. Assuming that we have a closed boundary. So please take note of that. Any question on that, please? No question? So we'll continue. So when you bring it here, beginning the end, beginning node, end node, or beginning where the surveyor took his spot height and where the next spot height started. If you do it, and then this is the length of each section. So if you now do vertical over horizontal, you get a slope. So these are the slopes. And then these are the corresponding area. You can see that catchment A and catchment C and catchment D are almost of the same size. Here, A, B, A, C, E are almost the same size. So if you go down into the table, you also see that that is reflected. So these are the area. But this is not the final area that you use. Rather, this is only the impervious area you're going to use, but this is the total area. Okay, so no need to go back to what we did yesterday. So let's go to the rational sheet, which is the exact table. So I want everybody to open this exact table. And after opening the Z table, you also open the chart of rational methods. So we said yesterday that your calculation sheet will look like this. Something like this. But here, from column 1, column 2 to column 6, is talking about wastewater. Column 7 to column 13 is talking about storm. You know, as a consultant, you can do your storm and your sewer, the same sheet or sheets. But then I've come here to split them into 2. So if you split them into 2, this is what you're going to have. This is for the storm, and the next sheet is for the sewer. This is the storm, sorry, and this is for the sewer. Are we good to go? Okay. So here you list the pipes. Okay, the pipes are pipe A, B, C. In real life, this can be this can be up to 1,000. Go ahead, sir.
Okay. Okay.
Network is poor.
Thank you so much. Yeah. All right.
Are you asking a question? Not at all. Okay, let's continue. So here, you will see that pipe A, the beginning, the end, the length is here, and the slope is this. If you go to our chart, our table, okay, here's our table. He said that the slope is 1/200. So if you do 1/200, you get the slope. 1/300, you get the slope. So these are the slope here. Normal slope. Slope is dimensionless, unitless. Okay. So if you convert it to percentage, it's going to be what? 5%, 0.5%. If you convert it to 1,000, you know this thing is. If I'm asking,
hello, yeah, you have collected it, Abby. Okay, and drop it and take it to the house.
If I ask you to convert 0.05 to percentage,
Hello, is the meeting still on? Sorry.
I suppose there's a technical issue here.
Yeah, I'm back. I think MTN has issue. I've switched over to Airtel. So let's continue. Apology, please. So you can see we have put them in table in this in the proper perspective. So all this we did all this yesterday, how to generate this. But for the benefit of those who are not here yesterday, the first thing you do is you characterize the catchment. What's the consequence of catchment? Based on the composition of the catchment, you assign the corresponding peak runoff to them. At the end of the day, you use the mean weighted average to get the average runoff. Then for the design storm, we chose 10 minutes. Population density, 100 capita per hectare. Water consumption, 130 liters per capita per day. Peak factor, 2. Parasite water factor, 0.1. Pipe roughness coefficient, K equals 1.5. So we all did this yesterday. I really don't want us to dwell much on it. But then it's good for us to see how we generated what we're going to be using. So to generate the wastewater flow per hectare, what we did was to multiply the wastewater flow per capita, multiply by the population density, multiply by the safety factor, add infiltration factor. And that's how we got this. This 86400 is that you have to convert day to seconds. Because at the end of the day, we want to get our unit to the smallest measure, which is liter per second. So if you are doing pipe sizing in SI units, your flow or your discharge should be in liter per seconds. Please take note of that. Then how do we choose our rainfall intensity? We say it's a function of N and D, the duration and the frequency. And here is what will guide us to choosing duration. If you are designing for rural area, you choose a duration of one year. If you're designing for flooding, you choose 10 years. For residential area, you choose 2 years. But if you're designing for flooding, you choose 20 years. For city center, you choose between 2 and 5. But if it is designed against flooding, you choose 30, and so on and so forth. Okay, I think we all discussed this. So for those who didn't come today, I give you indulgence. When you read all these things, you will definitely come to speed with it. So let's go back to where we are. So now I have written the pipe sizes, I have written their lengths, their slope becomes the vertical height over the horizontal height, which is the gradient. Somebody called it gradient yesterday. So the gradient will give you this. Then if you multiply by 10, it will give you in per thousand or per mil. Engineer Eddie and John, do you have a question?
Yes, please.
Okay.
Please, I just want to clarify on the slope. Let's take, for instance, the pipe A. If I'm assuming that 2.3, which is the start, and 2.2, which is the end, are spot levels.
They are not spot levels, sir. Please.
Oh, okay.
They are okay. Notation, yeah. But in real life, they are meant to be spot level. Someone asked a question yesterday. They are meant to be spot level. If they are spot level, it becomes 2.3 minus 2.2.
Minus 2.2, okay.
Divide by 500.
Divide by the length, 500. Okay.
Yes, yeah.
I wanted to clarify that. Okay.
And that's why thank you, sir. That's why I said in every infrastructure work, the first person that goes to site is surveyor. In fact, if you want to do a good infrastructure work, be it sewer, stormwater, telecommunication, they should have done the road design. The road design should have been done because you have to follow the right of way. And the road design, even the cut and the fill, will follow the road level. So here, in real life, column B and C should be the spot height. Thank you. So after getting the slope, how do you get the discharge? The discharge will now be the area multiplied by the peak runoff multiplied by the rain intensity. We discussed yesterday. Okay? We discussed yesterday. The discharge is here. This is discharge. And how do you get the discharge? The population equivalent multiplied by the safety factor, which is the peak factor, multiplied by the wastewater flow. Let me give you an instance of what I mean. In a 3-bedroom bungalow, somebody asks you, what is their wastewater flow? What wastewater are they generating? And that's what wastewater they're generating is also the water intake. So it's vice versa. So for 3-bedroom bungalow, how many people do you think can be in a 3-bedroom bungalow? Let's say 10 people. We now ask ourselves, what is the water demand? Due to WHO. WHO said between 100 and 250. And then WHO, yeah, okay, to 150. This is a new standard. So therefore, let us choose 100. So we choose 100. And then let's assume a safety factor or peak factor of 2.0. Therefore, the 3-bedroom bungalow, the water demand for the 10 persons becomes 10, of course, multiply by the units, multiply by the safety factor. Okay, we're going to get 2,000 liters per day. But day is equal to 24 times 60 times 60. I'll give you, this is 400. Yeah, this is 400. So by the time you do the calculation, divide everything, you should be getting something like 0.23 liters per second. So that becomes the flow of wastewater into the sewer system. Or it could also be the flow of water into the consumer units. So whichever way, it depends on whether you're looking at wastewater or you're looking at drinking water. So let's go back to the Excel. So if you go to the Excel now, so for this one that we did now, sorry. So for this one we did, we now decide to say, we don't know the value of this 10, but we are giving that the place will not contain more than 100% for every 1 hectare. So if this is what it is, then it means that every 1 hectare will now generate 100 times the flow per person. 100 times maybe the safety factor 2. That will be what? 20,000. So that means if you look at it, it means that 10 units of 10 bedroom will enter is the same thing as saying 100 persons per hectare somehow. Yes. So is that understood? Any question? Can go on. Okay, let's go back to the Excel. So you can see this is now the wastewater flow we generated. Here they are. Because the next thing we'll do is how we got it is that for this one we assumed 130 here from what you're giving. We assume 130. Okay. Yeah, this is how we got it. here. 130 times population density, you convert it to the appropriate unit, multiply by 2. So we use a safety factor of 2. Then we'll finally add infiltration water, which is not too, which is due to the leakage of water into the sewer system. So here, after getting the flow here, so if I multiply this, so if you multiply 15.63 by the discharge, that means discharge should come before this. So you now put it here. Good. So, oh no, not even there. Yeah. Go ahead, sir. I want to ask a question. I'm coming, sir. Just hold on. I'm trying to modify this. Okay. You want to ask a question? Go ahead, please. Go ahead. Go ahead. Okay. Okay, let's continue. So you can see if you multiply this by this, you get this. So I tried deleting this one, but it's giving me error because the cell has been fixed. So if you multiply this times this, you get this. 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 So this is the area. Remember yesterday we say CIA, the universal formula is, let me come again. So that Q is equal to AV. Okay, or you capitalize them in capitals. Where A is equal to the area, V velocity. Okay, so if you multiply the catchment area and this velocity in storm can also be now intensity, the rainfall intensity. So this multiplied by this will give you this. This multiplied by this will give you this. So after you have gotten all this, you now do summation. So catchment A is on its own. So catchment A remains. Okay. Catchment B will now be, this is the volume for catchment B, but the flow at catchment B becomes A plus B. This plus this gives you this. Catchment C is on its own. So it remains this. After multiplying by this. But when you now go to catchment D becomes catchment C for catchment. No, it becomes catchment B plus C plus itself. Let me show you what I mean, please. If you look at this very well, if you look at this layer very well, catchment B is now catchment A plus itself. Catchment D is now catchment B plus catchment C plus itself. Catchment F becomes catchment D plus itself. Why is it so? Because it's accumulation, it's aggregating. As water is flowing downstream, as it's getting more tributaries, bringing water into the main trunk, the pipe is getting bigger, the flow is getting bigger. That's why those who live in downstream, areas are the people most affected by flood. Because upstream is mainly expensive. So people tend to live at the downstream. And there, by the time rain gets there, water gets there, is already on full-fledged velocity. So what do you have here? So here becomes this plus this, give you this. This 15.67 is this plus this plus this. Okay. So if I multiply this by this, if I multiply this by this, I get this. So this is, let me call it 7A. If I multiply column 7A by this, it will give us this. Okay. Okay, so it doesn't see the catchment I'm doing. Oh, I didn't share the screen. Sorry, sir. Please, here are the catchments, sir. Catchment A, B, C, D, E. So as catchment A gets to catchment B, it increases. It pours its own content, its own discharge into catchment B. Catchment C gives its own discharge into catchment D. So at catchment D, the discharge is getting bigger and bigger. So if you look at our table, you find out that it just keep getting bigger and bigger and bigger. So that is one thing that will help you know that you know what you're doing. So after getting this one, what do we do next? We now add up. Add up. Catchment A cannot add to anything. Well, catchment B must add up to catchment A. Are we getting it? Then, after that, at this point, you can go to your chart and design your pipe. And that will be the end of the work. So when you go to pipes, there are about 4 major pipes we consider in engineering. Concrete pipe, ductile iron, asbestos ceiling. So all of them have their own respective frictional factor. But today, we'll be using one developed by the University of Stuttgart based on Euro code and German code. So I go to charts. You see there are 3 charts there. One is 0.1 coefficient of runoff, coefficient of roughness. One is 0.4, and then one is 1.0. Now you didn't see 1.5 because 1.5 is on the high side because the 1.5 will be a very rough concrete, but a moderately casted concrete should be around 1.0. So can you help me open the nomograph call 1.0? Can you go to your material, everybody, please? I asked us to print this today. Anybody that printed it is a very good student. So I'm opening it. Yesterday, I tried to explain to us how to use this chart. Very simple to use. Okay, you give you two parameters, it will give you two parameters. Is that not cool? So here, what parameters do you need to give him? You need to give him the flow or the discharge on the horizontal, and you need to give him the slope on the vertical. So the answer will come up, it will give you one of these diameters of pipe, or it will give you one of these slope pipe. So in our case, the first one is 6.28 at 5 per mil or 0.5%. So I'll come here. Six point something. I'll draw it. It's about 5. The meeting point is between which pipe and which pipe? Can somebody help me? Put the answer in your chat box. Open your monogram. At a discharge of 6.2 and a slope of 5 per mil, what is the answer, please?
125 mm.
Sorry?
In between 100 and 125.
Good. Who again?
In between 100 and 125.
Any opinion?
Pipe selection.
Pipe selection.
Is it now? Okay.
Okay, please unmute.
Okay, so between.
So here is fall between 100 and 125. So we choose the biggest, the bigger of the two. That's what we say yesterday. Then if you look at this also on the horizontal, you see that it's falling between two lines too. 1, 2. On the left to right, it falls between this and this. Between this right to left, it also falls between this and this. So here I fall in, you trace it. So you can see this is about 0.5, no, 0.6. So here, the velocity is 0.6, and the pipe size is 1.125. So I just want us to spend 5 minutes now. I want this class to be interactive and practical. Can we spend 5 minutes and get me the pipe size, even though I've written it, but confirm the pipe size, these pipe sizes. So can you do the one for 8? Somebody do the one for 8. Another one do the one for 5. Another one do the one for 15. This one 15, I doubt about it. Give me the right answer. So please, can somebody confirm any of this? So let me do the second one. The flow here is 8.46. So I'll go to the chart. And the velocity is what?
Three 3.3.
3.3. Thank you, sir. Please, I will appreciate if I appreciate such response. It goes to show that people are following. Mouse is not moving. Okay. So if I go to 8 point something, which is here. So 8, I'll trace it to 3.3, somewhere here. I'll go and I'll be getting a value here, which is almost like like 750, that 150. Is that okay? So let's do some together. Let's do some together, gentlemen. Please, I want it to be practical. I want the class to be interactive. So can you do for the remaining pipe size? Confirm on your own that you've gotten them. Open the Excel. Can you read the charts, please? Read the chart and get me number C. Look at C.
Okay, sir.
So I'm waiting. I'm giving us 10 minutes. Confirm these pipe sizes, size them. Confirm that these sizes are correct. So just the discharge versus the velocity. Using these charts, size all the pipes for the sewer network. Please, only 10 minutes. I'm here. Can ask me a question, please. Thank you. Open the nomograph in your file. Any feedback? Are we following? Are we confirmed? Can we comfortably say we can use this nomogram, these charts? That's the major takeaway from this training. Your ability to use your flow and your slope, and you're able to determine the pipe size. because it's that pipe size that you go and write in your detail, in your report, and detail it in your AutoCAD drawing. So the how to generate the discharge or the flow is what we've discussed yesterday. So let me know if there's anybody that have any challenge on that. Any challenge? Have we confirmed? I wish I can remove all this and keep it blind and ask us to do it. So do you understand how we got all this? Does everyone understand how we got this? How we sum up this?
Catchment C goes between 100 and 125.
Is it catchment C or pipe C?
Pipe C, I'm sorry.
Thank you. Thank you. Between 100 and 125, but you choose 125 because engineering, you choose the worst case scenario. And I said in infrastructure design, it's better to over design than under design. Now, even on the long run, you might not be able to use 125 for two reasons. Number one is that the code says the minimum you can choose is 150. You can use is 150. So, but it shows you that 125 can actually do the job, but you are going to choose 150. Besides, we don't have 125 pipe in the market. It's even 150 that we have, which is 6 inches. Okay, so Eddie, what's the challenge? Oh, okay. Okay, just be patient. You joined us today, so it might not be easy for you, but study this chart. The only thing I want you to understand is that what we did here is aggregation. When everything on chart A, catchment A will flow into catchment B. Catchment C will flow into catchment D. So as the water is flowing downstream, it's getting bigger, the flow is increasing. And so when you are doing your design for piping, you don't just say the water flow from A to A, no. Yeah, you can do that one for A, but when you come to D, it is the accumulated flow coming to D that you use. And that accumulated flow is what we try to do here. Here, this is what we got for A, this is for B, this is for C, this is for D, this is for E, this is for F, this is for G. But then when we are now accumulated them, this is now A, then for B now becomes A plus B. Look at it. If you click on the cell, you'll be getting how the cells you're getting. Then when it comes to C, C is on its own. That's why you see C is equal to C. No changes. But when it comes to D, D becomes B plus C plus itself.
Okay.
B plus C plus itself. It gives you this. So if you look at it diagrammatically, the flow in D is these three people.
Yeah, yeah.
But this B has already taken care of these two. So it becomes this value B plus C plus D.
Okay.
This is one of the most important concepts in flow design. If you understand it, you can understand water reticulation system, you can understand stormwater system, you can understand sewer system. So anything by flow, you will understand it. You know that, look, as the triple trees are coming in, the stem is increasing. Gentlemen, this is common sense.
Yeah.
But it's so difficult for a lot. That's why when you see some design people do, they will use uniform pipe sizes. And you begin to wonder, does it mean that this thing is not increasing as it's going downstream or as it's going upstream? If it's water reticulation, as the pipe is getting towards the elevated tank, it's getting bigger. That's why most people that design their houses and you use 1 inch pipe to take water from the overhead tank, you have water problem if there are more than 20 people in that house or more than 10 pipe taps. So ideal thing is to use about 2 inches pipe. And if it is where there are many people, use 3 inches pipe for the main coming from the overhead tank. When it now gets to the different houses, you can take it down to 2 inches. Then when it enters your houses, it can go back to 1 inches. So you'll be with us, sir. When you go to the material, you'll have it more.
Yeah.
Okay. So that is what is there. So when you do it, you find out that at the point of the treatment plant, which is point H, the pipe size is now biggest because by then it has accumulated flows from the different districts. Like in Abuja, the wastewater treatment plant in Whooper, when the wastewater is getting there, the pipe size will be as big as 600 or 450. But in Wuse and all the upstream areas, it will be 150, 250, 350, 400. But once it's getting close to the treatment plant, which is point H, it becomes bigger. That's why if you look at point H, the discharge is about 30 liters per second. If you now go to your chart, let's see what it is. I go to the chart, I go to 30. And this is 30 here. And what is the slope? Can somebody help me with the slope? What's the slope? What is the slope of pipe?
1.7.
1.7. Thank you, sir. So I come here. I go here to 1.7. What did you get, gentlemen? What did you get? What did you get?
In between 250 and 300. So I'm going to
but engineer, for me, I think I should advise you to go to 250. Why? Because it's too close to 250 than it is to 300. It's just common sense and experience. But if you choose 300, it's not bad, but it might be oversizing. Are you with me, sir?
Okay, sir. Yes,
yeah, it's too close. Yeah, try and be conservative this time. So I'll choose 250.
okay.
So is everybody in class together? Is this okay so that I can move forward? Have you understood it? Have you grasped it? So this is how you size your sewer. The input parameter again is the wastewater flow. And wastewater flow is just the inverse of the potable water intake. Thank you, sir. And I said in Germany, when they supply you water, they charge you for wastewater because of law of continuity. All of us know that equilibrium balance. If I give you 100 liters of water, are you going to throw it in the sky? Are you going to dig the ground and pour it inside? No. You are supposed to also discharge the 100 liters back. So when they charge you for utility in Germany, they charge you ×2 for water, knowing fully well that if they have supplied you 100 waters, they will be expecting 100 liters of wastewater. So that is why the input parameter for the water is also what we use for our listing. So then to get further, how, somebody say same in UK. Good. So that means it's European thing. Then if you now want to get how I got all this, I'm sorry, what am I saying? You now go to the folder, what I've shared to us. There's something I share with us, catchment calculation. Yeah. Good. Look at it. So how do you calculate a pipe size? So you make your, as engineer, you make your assumptions, your takeoff calculation. So the first thing we said here is that we assume that the wastewater demand, or water demand, sorry, not wastewater, water demand per capita, per person per day is 130 liters per capita per day. We now assume that the population equivalent, because that place is a virgin land, it is not 3-bedroom or 4-bedroom that you can count and know how many persons there, but they're giving you the land use. The land use says 100 people for every 1 hectare. Okay, which is basically 10 people per plot, if you look at it very well, because it's 10 plots, 10,000 square meters give you 1 hectare. Then we chose a peak factor of 2. Peak factor varies between 1.3 and 2.5. I said it's in our test. It's also in the code and standard. Then we choose another safety factor, which we call the parasite water. I said that the parasite water is those water that infiltrate your sewer system unknowingly. So you make provision for it. You don't assume that your sewer line is airtight. It's not possible. Once in a while, no. 2 is just what we choose. Somebody in John said Is P factor of 2 a constant for worst case scenario? No. It depends on the number of population you are designing for. It's in our material. If you are designing for between 1 to 10,000, you choose a higher one. If you are designing around 1 million, so this value, as far as I know, is for about between 100,000 and 1 million people. Now, let me give you one story. Abuja, the P factor that was used in designing Abuja was 2.3. Quote me anywhere. The Germans, when they designed Abuja in 1978, they used 2.3 as a P factor, and they were targeting Abuja to be 1 million people in the first 25 years. Yes. I'm not talking about the outskirts, the main Abuja city center, capital city, FCC, federal capital city is 1 million. So they choose 2.3. So many people in those days in NSC, when they do something on water, somebody will come and tell them that the water demand for Abuja is 230. For me, as a water expert, I know that they were only multiplying the safety factor. But the real value that was used was 100 liters per capita per day. I can defend it anywhere. Because even in Germany today, in places like Hamburg, the water demand is about 116 liters per capita per day. Places like Munich, Stuttgart, down south, they are still using 120. So the average water demand per capita per day in Europe is about 120. It's when you're going to America and Canada that you see it going up. The UK, Engineer Eddie, I don't know what it is in the UK, but I guess it should be between 100 and 150, which is also the WHO recommendation. Okay, so let's continue. Then, so this is our assumption, and then this is our drawing, using rational method. So what did you do? You put it all on a table like this. You must put the table like this. These tables look simplified, but in real life, yeah, okay, it says UK is Euro standard. Yeah, Euro standard should be 120. Yeah, should be that. Should be about 120. Well, let's prove ourselves, right? Water, specific water demand, that's how to put it. Specific water demand per capita. Okay. Britannica say 250. It's not true. It's too much. But let me put something here. In UK. Yeah, UK say 150. So you can see that UK says 150. So that's by the way. Okay, so let's continue. But UK say 150 because UK is already inside on top of water. If you come to Nigeria, there are some places that they hardly see 50 per day. So if you're designing 100, that system will be designed. So use 100. If you're designing above 100, you have to put into consideration the availability, the energy cost of extraction or extracting the water. And all of us know that the more difficult it is to source water, the less people consume that water. Okay, so after the diagram, you create an Excel sheet and bring up everything in form of a table like this. After that, we create the catchment characterization. Let us know what the peak coefficient to use, because the peak coefficient is what influences. When the peak coefficient is needed in storm, not in sewer, in storm. Then for the sewer, it is just the 130 plus the number of persons per hectare plus the peak factor. Multiply all of them together, you get your flow. And this is where we did it. So we multiply all of them together, convert them to liter per second by dividing it by 86400. You get your 0.401 liters per seconds per hectare. And that is it. So you now move over to the storm. We move over to storm. When it comes to storm, we said the formula for storm is now intensity times area. Remember our formula, the universal formula in fluid mechanics. Q is AV. Q is area times velocity. Q is the size of the aperture times the velocity. Okay, but the area here is meant to be the contributing area. So we'll now multiply it by the peak coefficient to get the A impervious. So at the end of the day, we multiply both together and we'll get our Q. So let's go. So this is how we design our sewer. Okay, 130, 100 capital per hectare. Peak factor is 2. Infiltration water is 0.1 for every hectare. So for catchment A, what is the area of catchment A? Catchment A is 115.63. Therefore, the discharge that catchment A is contributing becomes QV, which is 130 unit for one person times 100, which is the population equivalent, times 2, which is the safety factor, then plus 0.1, which is the infiltration water. The answer will now give you 0.401 liters per second per hectare. If you multiply this 0.4 liters per hectare times the reduced area, sorry, there's a mistake here. If you multiply these two, you can't get that. Okay, there's no reduced area here, yes, it's for storm, in order. So if you multiply by this catchment, why I multiply by this catchment? Because the answer is in per hectare. So to cancel out this hectare, we need to multiply by the area that this sewer is coming from. So if you multiply by 15.63, you get 6.29. So with 6.29, you move over to the chart. So what do we do from the chart? We read 6.27 or 2.29, whatever, whichever. It's in PDF, so it won't change. You now read 6.27 against 5 per 1,000. Okay, the slope is 0.5, but from our chart, we are going to read it against 5,000. So if you do that, you now, okay, look at where I did it. So this is it, 0.5% or 5 per 1,000. They are the same thing. So if after doing it, you now get the value as 125 millimeter. But I quickly said here, use 150. Why are we using 150? Because that is what the code recommends. Well, that's the recommendation of the code. So after that, we move to catchment B. We move to catchment B. For catchment B, the same thing applies. 130 multiplied by 100, okay? Then multiply by 2, which is safety factor, add 0.1. That will give you the value for catchment B. So, and so on and so forth. So this is how we'll now do for all of them. And that's exactly what we have done. Look at it. It's exactly what I have done. Any question? Any question? Please, those that are joining us for the late today, open the rational Excel sheet called rational sheet modified. So we are trying to show how we got this. Now, as I said it before, it might look simple here, but in real life, this thing will get to about 1,000 pieces. So you can see that there's a lot of work in it. So, but this is just only for pipe A, pipe B to pipe H. But in real life, you can even see like 500 pipes. So you have to design all of them. So this sheet will be so huge. Any other question? If there's no question, then we'll move to the storm. If there's no question, we'll move to the storm. But have it in the back of our mind that what we've done now is just between column 1 to column 6. So you can see this is column 6. That's how we'll stop. So Next thing you now do is you design your stormwater. Any question? Okay. The next thing we do is we move over to storm. Move over to storm. So storm is just the same thing. The first 5 columns are the same. You can see this is slope in 1,000. This is slope in percent, which is per 100. The slope unitless, the length of each section, the end, the start. So where things now change, okay, even the area becomes the same. Where things now change is that in the sewer, we aggregated the flow, but in the storm, we aggregate the area. So it's the same thing. We add up the area. Why are we adding up the area? Because we said that the storm is CIA. The formula for storm is CIA. Q is equal to CIA, where C is a constant. I or R. I or R is the what? Intensity. And A is the catchment area. In this case, we call it the reduced catchment or impervious. Okay, so now, if you look at this formula, this one is constant. The C is constant, the intensity is constant. So the only thing that will vary is the what? Area. So as you are going from upstream to downstream, the area that is contributing to runoff is increasing, just like we did in the last one. The area that is contributing to runoff. So if we come to catchment B, the total area becomes the catchment A plus catchment B, which is this big. When it comes to catchment D, the catchment that is being supplied water, the catchment that is water is flowing into becomes this. Are we together? So this one flows into this one, C flows into D, E flows into F, G flows into H. That's why if you want to do anything upstream, you must consider the safety of people downstream. Because once the discharge becomes big upstream, just like what happened in Nigeria, 2013, all the dams in our Cameroonian border got filled and they released the dam. And guess where it's going to hit? It was hitting people. Bayelsa, and then maybe places like Lokoja, because it's a almost lying flat. Okay, so we move to the stormwater. So stormwater, when it comes here, you see that the area here is 15.3 and the area of A is 15.3. But the area of B is 5.7. But because it is a tributary, A is a tributary to area A, or A is upstream of B. So the value for B becomes this plus this becomes this. This plus this becomes this. Then the next one is number C. C is on its own. So the sum area remains the same. C, look at C. C is on its own. In fact, if If C does not contribute anything, the other ones will continue. Then D is now, what is the value of D? Can somebody help me? D will now be B plus C plus itself. So 3 plus 14 plus itself. So D becomes B plus A plus electrical energy itself. You now get 39. E is E. E has no tributary, it has no upstream, it has no downstream. It has no upstream, sorry. It remains this. But F becomes what? D plus E plus F. So that is that. So here, G is on its own. So G remains G. So let's continue. So after doing that, aggregating, you now multiply each area by the runoff coefficient. This runoff coefficient, we did it in detail yesterday. Very, very important. Because it is not all the areas that are contributing to runoff. Depending on the characterization of that area. Some areas have green, some have road, some have roof, some have sandy soil, some might deep percolate, and so on and so forth. So here, you can see, if you multiply this by this, you get this. Multiply this by this, you get this. Multiply this by this, you get this. Okay, so this becomes the effective area. This is now the area contributing to runoff. So from 15.63, because most of the areas are green, the peak factor, the runoff coefficient is only 0.37, meaning that 60% of the water that falls on this catchment will go as infiltration. They will not flow on the surface. So finally, we now multiply this . So we now multiply, this is CA, and we say CIA. So this is our A, our I, sorry. So if you multiply this by this, you get this. How did you get this? How do we get rainfall intensity? You get rainfall intensity from your IDF at 15 minutes at the reasonable return period. I expect a question from there. Did you understand it? How we got our rain intensity?
Yes.
There's no mention of one chart yesterday, sir.
Yeah, look at it. Yeah, under Nigerian Code of Practice. Yeah, Nigerian Code of Practice, volume 4. Or, you know, in the past, what people do is that you go to river basins, go to NIMET and start looking for data. But the minister, and Kashim Ali, during his time, they came up and came up with this highway manual, highway code. So assuming I'm doing Yola for instance, so I'll go to Yola. I'll ask myself, am I designing for flooding or for normal surcharge? I'll say surcharge. I'll ask myself, is it a rural area, residential area, city center, underground? What is the risk associated with that? Okay. Some area, if there's flooding, you lose billions. Some area, if there's flooding, you lose nothing. In fact, you gain something. Okay. So here, 15 minutes rain And let's say we're doing for 5 years. This my screen is too much. Let's say we're doing for 5 years. So I'll come here, I'll read 15 again 5. That's giving me about 126 for 5 years, for 5-year rain. 5-year rain means that should be the value for city center or for urban areas. Okay, city center on urban areas. So I'll pick up the rain intensity there, convert it if need be, and then come here and dump it. So my CIA becomes intensity multiplied by the area. So you multiply this by this, and then multiply by the factor to get this. Is that understood? Any question? Any question? Now, if you look at this, the flow is now this. So, but what I did here was to divide this by 0.9. Somebody asked me, why do I divide it by 0.9? It's just another safety factor. The reason is that I'm designing underground pipe. And when you're designing underground pipe, your pipe should not flow full. If this is a pipe, let's say a circular pipe, water should not exceed 70 to 90%. So here is 10%. So the code says you should give small space so that the thing will not, because if you flow full, if there's any surge or any water hammer, the pipe will rupture. So normally the standard says 0.7 to 0.9. Your design water level should be between 0.7, which is 70%, to 0.9, which is 90%. So what I now did in this column was to say, I have gotten this value. Yes, this is okay. But I need to put a second level safety factor on it. So I divide this value by 10%. You know, some of us will agree with me that sometimes when you do your design, you multiply by 1.2. That 1.2 you're trying to multiply with is just an additional set, just to be sure that you didn't make mistake. So when you do this now, it will now give you this. So from here, you now go to the chart. So when I go to the chart, I'll do the first two, and I'll leave us to do the remaining one during our break. We're going to observe a 10 minutes break. So now, the first one is 800. So I'll go to my charts. Meanwhile, let me say this. The major thing you need to learn how to do is how to calculate this sheet. For the chart, there are hundreds and thousands of charts online. I have 2 here with me, and I will put it in our folder. But if you go through, the ones I have is the one from University of Stuttgart and the one from Federal Highway, Federal United States Federal Road something. Okay, I'll find the appropriate exact name. So this is 800. So I'll go to 800, and the slope is 5. So I'll go to 800. So 800, here is 800. Sorry. I'll go to 800, this 800 against 5. Here, you can see between 700 and 800. So I'll choose 800. I'll come to the second one, 1095. This is 1000. It's not 1100, so I'll go to 1000. I'll go up. I get to 5. 900. I want to grade the indulgence of everybody to practice this thing because that is I want you to practice and get it right. And once you get it here, let's say 1000, 2.5, somewhere here. So the slope, the velocity there is 1.6. So I'll just go on the left, on the right, on the left, down. I'll see the corresponding velocity. Then let me go to the third one, 730. Common sense will tell you that anything that's less than 800 should fall into 800. So 730 now, I'll go to the chart again. Okay, so 1000, can read it up to 1 point something. It's giving me 1 meter pipe. So that is how you will size this pipe, all of them. So after sizing them, you now go and detail them, and that will be your stormwater design. So I'm going to allow you to size the remaining one, and that's from D. And when I come back, please, we'll resume by 4:40. Just 10 minutes break for you to stretch, drink water, do 1 or 2 things, and then we'll meet again by 4:40. Please don't go away. If you don't have anything to do, just look at this and let me know that you understand it. As when you have understand everything, I'll be a satisfied man. So please just take a look and know how do you get all these things. Look at the aggregation. How do they get the flow? And so 10 minutes starts from now. So I'll see you guys in the next 10 minutes. Let me pause the recording. But if there's any question before we go for the break, I would like to take that question.